All right, guys. So we're going to take a look at water potential. And this always freaked everybody out when we talked about it. But it's really a very simple equation. And we're going to go through it again. I'll talk you guys through it and take you through stepwise. The questions that we're going over are the same ones that are on Schoology on the Word document that goes to the review for this unit. So this is in the cell structures and transport review. So these are those specific equations. I'm just going to explain them through so you guys get a better understanding of it. So basically, water potential, what is it measuring? It's measuring the tendency of a solution to either gain or lose water from another solution. And so what scientists did is they came up with a formula that gives you a number that's expressed as a negative value. So water potential is always expressed as a negative value. Okay. The formula is using the Greek letter psi. So psi is water potential, and that's equal to the solute potential, which is basically the water potential of a solution. That's based on its concentration. We can calculate that using another formula, which I'll pop up in a second. This is always going to be a negative number. All right, it's always less than zero. Okay, you can never have a water potential or a solute potential greater than zero. Okay, the reason for that is pure water has a concentration of zero. You can't get any purer than that and have a plus number concentration. Okay, so as soon as you put a zero into the equation, your concentration is zero, your water potential automatically becomes zero because you're multiplying. Okay, and I'll show that to you in the formula in a second. The other one here is psi p, and psi p is pressure potential. So in an open container, pressure is equal to zero because there's nothing being put on it, and we just assume atmospheric pressure is negligible. However, when you enclose the solution in a cell with a cell wall, or if you put it in some kind of tube with a piston on it, like a plunger, that's when your pressure potential goes up. And it's always a positive number. So pressure potential is always a positive number. It's always above zero, and it's always working against your solute potential. All right, so to calculate water potential, okay, so if we want to figure out the water potential, also known as solute potential of a solution, we have to plug in numbers. It's negative I CRT. This little negative sign here, right? This is important. This is what allows us to make it a negative number. So just by default, it's a negative number. Now, I is the ionization constant. For something like sucrose and glucose, which do not ionize in water, it remains as a solid molecule. It's always 1. Something like sodium chloride, that can ionize into Na and Cl ions. That has a constant of 2. Okay, MgCl2, magnesium chloride, MgCl2, you have an Mg ion and 2 chloride ions, that would have a constant of 3. Okay, C is the concentration of the solution. That's the molarity. They will always give this to you in the question. So they will always tell you have a solution with a certain molarity. That's what you're going to put in for C. R is your pressure constant, and that's equal to 0.0831. Okay, this is given to you on the formula sheet as well. So it's nothing that you have to ever memorize. You'll have the formula sheet available to you. And the last thing is the temperature. And temperature is always in Kelvin. So whatever your temperature is in Celsius, just add 273 to that. Most of the time, you're either going to deal with a temperature of 295 or 298. It's either like 22 Celsius or 25 Celsius. Okay. And so by adding that to 273, that's what your temperature in Kelvin will be. Okay. Now, if there's no pressure applied and it's an open system, if you have, for example, a cell in a beaker of water, all right, that beaker doesn't have any pressure on it. So the pressure is considered zero. So your water potential is going to be equal to negative ICRT, which is your solute potential, right? So this is equal to WS plus WP. So if there's no pressure, um, that's equal to zero. If there is pressure, okay, then you're going to have this have a positive number, okay? And so that's the basis for the formulas, okay? The only time you'll ever have to add is if you have pressure, and you'll see that in one of the equations. Okay, so let's take a look at some of the problems. Oh, here's the other thing. Remember, it's always a negative number, so never fear the negative number. If you get something that comes up negative, For water potential, it's supposed to be. If you get a positive number, you did something wrong. You got to go back and do it again. Okay? All right, so here's some practice problems. So you have a situation here. You've got a container, okay, and you put a semi-permeable membrane here. It's only permeable to water. So on one side of the membrane, we have a 0.1 molar calcium chloride solution. On the other side, we have a 0.1 molar glucose solution. So remember now, calcium chloride ionizes in the water to produce 3 ions. Glucose does not. Now, if you go to your formula sheet, you know that glucose has an ionization constant of 1. Okay, so you want to calculate the water potential for each side of the membrane. So first we have calcium chloride, so 3 ions. So that means that our negative I is going to be a 3. So it's negative 3 because this forms 3 ions, calcium and 2 chloride. Concentration, 0.1. Put that in there. R is your pressure constant, 0.0831. T is temperature. Did they give us temperature up here? No, they didn't. All right, so what's your temperature? Always assume either 22 Celsius or 25 Celsius for room temp. Usually they will tell you the temperature. So let's assume, it's going to be 22 Celsius. Okay, so you plug those numbers in, and here's what you get. Okay, so on this side, we get negative 3 times 0.1 times 0.0831, and our temperature is 295. Okay, when you multiply this out, it's negative 7.35. Okay, now on the other side, you do the same thing. If you notice, these numbers are the same. The difference here is your ionization constant. Okay, this is only negative 1. So that gives us negative 2 point something. It got cut off. I don't know what happened to it. But here's the deal. The water is going to move towards the more negative solution. So you're going to see a net movement of water from the 0.1 molar glucose to the 0.1 molar calcium chloride. And that movement will occur until both sides have reached equilibrium. Okay? Water always goes from the less negative to the more negative number. Okay, remember in a number line, 0 is larger than negative 1. Negative 1 is larger than negative 5. Okay, so water is always going to go down the gradient from the higher number to the lower number. Okay, all right, let's take a look at another one. We have a plant with a pressure potential of 2 bars. Okay, and its solute potential is negative 3.5. So they've already calculated out the solute potential. So what is the resulting water potential? Okay, if you remember our formula, water potential is equal to WP plus WS. Okay, so it's 2 plus negative 3.5. Now, if you do your basic arithmetic, and if you remember this from 5th grade math, 2 plus minus 3.5 is going to give you a smaller number because you're going to subtract 3.5 from it. So what you should get is negative 1.5, okay, because 3.5 is a negative number, okay, and you're subtracting that from 2. So that brings you down to the negative side. So that is the resulting solute potential. I'm sorry, water potential. Okay. Now, this same plant cell, we're going to put it in a beaker. All right. So here's our plant cell, right? And we're going to put this in a beaker of negative 4 bars. Okay. And here's our plant with negative 1.5. Okay. And here's the cell wall surrounding it. Okay. Now, which direction will the water move? The water is going to move out of the cell. It's going to move from the higher potential to the lower potential. Okay, it always goes down the gradient from a less negative number to a more negative number. Okay, this next question, number 3, they're not going to ask you to do this on the AP test. This is a conversion. So basically, you've got the same cell. Now you put it in a beaker of sugar water that is negative 0.15 megapascals. Now, 1 megapascal is 10 bars. So first you have to convert this. Okay, so we convert this, and if you just do a simple ratio equation, we know that 1 megapascal is 10 bars. So what would 1.15 be? You do the math, and it comes out to 1.5. Okay, so which direction would the water flow? Okay. Right. And the answer is neither, because now you have the same concentration. Okay. So it's not going anywhere. Okay. That should be a negative number 2. So just didn't come up when I was typing it. Okay, let's go to 4. Okay, you have a root. So the root tissue has a water potential of negative 3.3. So we're going to take that root and we're going to put it in a 1 molar solution of sucrose. That's at 20 degrees Celsius. So we want to know, okay, what's our water potential of our solution and which way would the water flow be? Okay, so here's our water potential of our solution. Okay, we know it's glucose, so it's -1 is our ionization constant. Concentration is 0.1. We're at 20 degrees Celsius, so 273 plus 23 is 293. So it's -2.43. Now the root tissue itself is -3.3. So just looking at those two numbers, which direction does the water move? Will it go from the root, which is -3.3, to the beaker, which is -2.43, or will it go from the beaker to the root? Okay, and the answer is it goes from the higher potential to the lower potential. So water is going to move into the root. It's going to go from the beaker to the root. Now, what the potential tells you is concentration and the tendency then which it's going to gain the water. So you know just by looking at something, if it's got a more negative number, that root is more concentrated than the beaker. Okay, so even at -3.3 versus -2.43, that -3.3 is more concentrated. So water is going to move down the gradient towards the more concentrated solution. Okay, let's look at this one, which is, my numbers are messed up. So it says here, NaCl dissociates into 2 particles in water, sodium and chloride. So now we take this solution, which is in this question up here. Okay, here's the solution, right? And we put sodium chloride instead of sucrose. So what we're going to do now is we're going to change the ionization constant. This is going to go to -2. Now let's see what happens. Boom, look at that. By going to -2, we've now made our solution have an even lower potential. Okay, so now we have -4.86 being, which is a solution, and we put a root that's -3.3, right? Water is going to move out of the root, okay, because now the surrounding solution is much more concentrated. This is what happens when we use too much road salt or there's saltwater intrusion into the ground, which is happening on the south shore of Long Island. When you have too many salts going into the soil, um, this is what occurs, and water now moves out of the plants. The plants dehydrate and they die. Okay, that's the reason why using rock salt and road salt is so detrimental to plants. Okay, and so that's created um, a more concentrated solution on the outside. Okay, all right. Now we have a plant cell. Okay, with a solute potential of -7.5 bars. We put it in a solution that's -4. So we want to know what's the cell's pressure potential. Okay. So its volume is constant. So here's the important thing now. It's -7.5. It's put into a solution that's -4. So we know the water is going to rush into the cell, but it doesn't. It's prevented from rushing in. So now we have to think about pressure. Okay, what do we need in order to prevent water from entering the cell? Okay, it keeps a constant volume, which means it's at equilibrium. So that means that the solute potential is -7.5. What is the pressure going to be so that it's the same as the external environment? So we want to make sure that the cell is equal to the external environment. So the external environment is -4. So we just do simple math. We say, okay, external environment's -4. Our cell is -7.5, which means the pressure has to be a positive pressure of 3.5. And that gets us to a cell that has the same water potential as what's outside. Okay. Okay, next thing, we have a cell that contains 6 molar glucose. It is in equilibrium with its surrounding solution containing 0.5 molar glucose. What is that cell's pressure potential? So again, the same thing. Okay, so now we have to figure out the pressure of everything, right? An osmotic potential. So we know that our cell, this is the cell's osmotic potential. Okay, -1 times 0.6 times 0.0831 times 293. So we know the cell is negative 14.61. We know that the beaker is negative 12.17 because we just plug everything in. We're just changing our concentration. Okay. So now we have a difference here. So it's an equilibrium. So we want to know what's the pressure potential of the cell. So we just do the difference between 14.61 and 12.7. Okay, and 2.44 is our pressure potential. And we know now that if we apply the pressure of 2.44 to the cell, okay, we get a number that's higher, 12.17. Okay, and that tells us that the cell is in equilibrium. Okay, because that pressure potential is bringing it up to the same concentration as the solution that it's sitting in. Okay, I hope that helps. If you're not sure, stop, rewind, go back, look at this again. And you guys can always ask questions, through Remind and also through the video chats. Okay, that's it for this. Have a great day, guys, and we'll talk soon.